Okay, everybody. So Anthony Marrero here, and bringing to you Community Problem 1. So this is the first time I've made a video like this, so I'm a little bit nervous, although I have a job that requires me to talk to complete strangers and teach them English. So anyway, we'll give it a shot, see how it goes. I kind of like the video format, and I think this is a cool idea. I'll just say that. Um, and it really helps to explain something that you've just learned. That way, you really lock it in. So I really like that too. Um, so on to the community problem. Uh, Question number 1. So we have here the NBA experienced tremendous growth under the leadership of late Commissioner David Stern. In 1990, the league had an annual revenue of $165 million. By 2018, the revenue increased to $5,500 million. Okay, so by the way, that's a billion. That it 550 million is billion, so a little bit confusing with the language there, but we keep it like this in order to keep all of our numbers easy to put into the formula. So if we just use 165 and pretend that's a million, and 5,500 and pretend that's a million, that makes it a lot easier instead of having to write all those zeros. So um, number 1 is give a reason why modeling this data with an exponential function is appropriate. So I just have some notes here. Um, Now, a business revenue is generally not linear. So, like when a business makes money, it's not the same amount of money that they're making every year. And in fact, a lot of businesses lose money. It goes up and down, and it's not at like a steady rate up or down. So if looking at it on a graph, it would have a curve, right? Hopefully, if it's successful, curving up. And in this case, it's a curve that goes up. Now, um, why do we want to do this exponentially? So we have these two data points. We have 165 million and 5,500 million. And what I basically put here is the more money that you have, the more money that you make. When you are investing money, for example, the more that you invest, the more money that you're going to make. And for the NBA, they probably make a lot of money from tickets and advertising. And I'm sure they have a lot of monetary investments as well. But if we looked into what's going on with the team owners and different things that the association does, I'm sure they have other ways that they invest their money and it grows. And all of those types of investments grow by a percent. So the difference between exponential and linear is that exponential grows by a percent change, and it's a constant percent change, whereas linear is just a constant change. So um, now the growth, again, also the growth that we see is proportional to the amount invested in a business situation. So like the more you invest, the more money you make. So when we see a business growing and growing, they're going to have more and more money. So they're going to make more and more money as they have more money year by year. So um, to me, that makes sense why we would use an exponential function. Um, and really when we look at the data, we could see, if that makes sense. So moving forward, number 2 says we're going to write a formula for an exponential function, r of t, where t is years since 1990 and r of t is measured in millions of dollars. So um, over here, sorry for the messy handwriting. I hope you can read this okay, but we'll just start by explaining what is an exponential formula. So the way it's set up is just generic terminology here. We have f of t is equal to a times b to the t. Now, what does that mean? So the f of t is our output. Um, it's our y value. And when you're looking at a graph on the Cartesian plane, the y are the values that go up and down vertically. Okay, and a is our initial value. This is also called the coefficient, but uh, in our example here, our initial value is 165 million. So that's the money we're starting at, and we're going to see where that gets us depending on what year it is, right? So uh, T over there is our input, and in this case, it's the year. Okay, so 0 years at the start, 1 year the next year, and so on and so forth. And B is our growth factor. So that's the amount that it will grow depending on what year that you're at. So that's why it's raised to that power of the year. So maybe it's 1 year, you would multiply that number by itself by 1 or 2, and so on and so forth. So we're gonna use this to make our formula. Now, in our example, we're using R of T. So R is the revenue in millions of dollars, and again, T is the years since 1990. So we already know what we're starting at. That's 165 million. So we're going to put R of T is equal to 165 million. And we don't yet know our B, so we'll just leave it as B. And then we have raised to the T. Okay. So again, this just depends on what year we're looking for. We can always plug that in as our input and see what our output will be. So to solve for B, we're going to use this formula here. So what does that look for? How does this work? So what it takes is two values, okay? And we already have two value points or two data points on a graph. We have our starting point, which is, sorry to keep highlighting the whole thing. We have our starting point, which is 165 million. Now again, that's our y output, and we have 0, which is where we would start at the beginning of the graph, 0 years from 1990, and that would also be on the y-axis or at x equals 0. So putting this as a point, it would be 0, comma 165, x and y. And we're going to call this our first point, x1, and y1. And we could also call this T1 and R of T1 to help visualize how that will go into the formulas. Now, the second point, we have to do a little bit of math. Now we have this number, $5,500 million dollars, and this other number is 28. Now how do we get that? We just subtract our year, our ending year, which is 2018, minus our starting year, 1990, and we get 28. Now, what this does here is it is showing how just using the principle that these proportions are equal. So with an exponential function, we can look at the second output divided by the first output, and that proportion should be equal to the rest of the formula, the A, B, to the whatever input you're putting in, whatever year you're putting in, and same with down here. So those should be proportional one with another, and we'll talk more about that later at the end for question number 4. But anyway, we'll go ahead and we'll plug these in. So our y2 is over here, and I labeled them so I don't get lost. I get lost and confused, so I like to put the y2 underneath it, and that's 5,500 over 165. And then over here, you got to make sure that you don't mix these up. This 28 goes with the 550. And if you write this down, it's, if you're like me, it's easy to not get mixed up. So I write it down that way, I don't put the 28 down here. Okay. Now, when you divide these two numbers here, 5,500 and 165, you're going to get 33.33333 or 33 and a third. And this one here, the way that exponents work when they're being divided is you just subtract them. So first off, we do know uh, our A here. We know what A is, but we don't need it because this is going to get canceled out. Another principle of division. So A, if A is divided by A, you just cancel that out. And for this one, 28 minus 0 is still 28. So we have 33 and a third is equal to a B to the 28th power. And this is one that has confused me before. And you got to remember, if you want to know what do I do with that 28th power, how do I get rid of that to solve for B? What you do is you raise it to the reciprocal of that uh, exponent. So this could be pictured as 28 over 1. So we're just going to raise it. Don't multiply it. If you make that mistake, you're going to get the wrong answer. So you raise it to 1 over 28. Now, you got to use a calculator. If you try using the Windows calculator for this, you may have some trouble. There's a way to do it, but I don't like using it. It messes me up. I use GeoGebra, which I'll show you in a minute. And you would also raise this 33 and a third to the same 1 over 28th. Now, when you do that, B is going to equal, or B to the 28th power is going to equal B, and 33 and a third to the 1 over 28th power is going to equal 1.1334, and then a bunch of more numbers after that. I just rounded it to the fourth decimal, so this is our B value. Okay, so now we have everything for our formula. So if you look here, our formula would be R of t is equal to 165 million times 1.1334 to the t, to the tth power. Now, again, let's just talk about this here. So R of t is our output. That's the revenue in millions of dollars over in the course of so many years. So if you want to know how much is the revenue over 8 years, your t would be an 8 here. You could just plug it in, and that's what the purpose of a function is in the first place. Now, 165 is our initial starting value. That's where it's going to cross the y-axis, and that's what we're interested in. So that's what data we've gathered or what data's been provided to us. And then we have our b value that we solved for, and again to the tth power. So there is the formula. Now, why does this make sense? When we look at our formula, we want to also say, like, is this right? Does this make sense? And it does make sense because we know that given the data, it looks like this. It's growing, right? We want to see growth, and with this number for b, it is greater than 1. So that means it's going to show a growth with the data and with a graph. If it was between 0 and 1, that would show decay, or it would show decreasing values. The business would be losing money in that example. So this makes sense. Okay. Now, for number 3, the question is, during what year did the revenue of the NBA first surpass $1 billion? So we can do a numerical or a graphical solution. Now, this one, it's about as easy to do the numerical one, but I just always go to the graphical one because it's like using a calculator, or it is like using a calculator. It's just, for me, it just seems like the easier way to go about it most of the time. But we got to know how to do both. But what I did here is first I just wanted to explain because we want to know, we need to make sure we understand that in our data set and or in our graph, the way that we've scaled it is we said that one, the number one is equal to 1 million. So the number 1,000 is equal to 1 billion. Okay, so we need to find where does our graphed function, or where does our curved line, where does it reach $1 billion on the y-axis as it goes up? Where is it going to hit that 1 billion point? Okay. Now, again, first I graphed this. So what I use is GeoGebra. Desmos is another um, a good tool to use. I'm not sure which one I like better, but I've been using this one. Sometimes there's some bugs. I don't know if it's my computer or the website itself, but um, it really helps. And I don't even have a TI 80 anything calculator. Maybe I'll get one eventually, but this is what I use. And if you go to their website, geogebra.org, at the home page, you're going to see over here in the ready for test section, there's going to be a graphing calculator and a scientific calculator. Now, I use both of these. Okay, so um, if you click on the graphing calculator, it's going to open up this page, and it's going to be blank. I already have some formulas entered in here. Um, Now, this first one, I literally just typed in here the formula that we found. Now this f of x equals, it automatically gets typed in. Like I'll just show you an example here. I just typed in 165, and I like to do the parentheses just like we write it down, 1.334, and then you press your arrow key to the right, or you click over here. And the way I do it, you can use the calculator down at the bottom, but I hold shift and press 6 for the little caret, and that will raise my little cursor up here. And what we're looking for in the exponent is t. Now, I believe I can put a t here. I'm going to try it. X and t are like two so it worked. If you try to do like another letter, it might not like it. I usually just do X because it works. So just remember that if your question on a homework assignment uses a weird letter like I, and you try to type that in, it doesn't work. Just use X or T, or you can play around with that and figure it out. But anyway, it'll automatically put in your P of T equals, or if it's the first one, it's going to say F of whatever. And it's going to change your parentheses to a times because it means the same thing, and that's just what the calculator likes. But anyway, I'm going to delete that. We don't need it. I already have it up here. In this green line, you can click on these to make things disappear and appear. This green line is our graph. Now, where we are in our window, you can hit this home button, and that will, if you're over here on your graph and you hit home, it's going to take you to the center of your graph. And it's going to take you really zoomed in. You cannot even see your graph. Now, over here in the settings, there is a place where you can manually type in your window settings like you would on a calculator. I usually don't do that. I usually just, use my mouse wheel and zoom out. However, like if you're really trying to move this thing far, zoom out a lot, it's better to type it in manually. You just put in the values. You'll just put in the values that you're looking for here. So we're looking at for our y. We don't care about less than 0, and we want to go up to 5,500. But let's put in 15,000. So we can be zoomed out a little bit, and let's put in, I don't know, maybe 5,000 here. And for our x, we're not going so far, we're just going so many years. So we get 0 years, but again, I want it to be zoomed out a little further. So, we could say minus 10 years, and we could put over here, 50 years. So I'll hit enter, see if that works. I usually don't do it this way. But it's actually kind of off of what I'm looking for. So anyway, I just used the mouse, not too far off. So anyway, you can see how you can use that. You can. I probably should have put my y value smaller. But anyway, there is our graph of our function. And what we can see here is that at the year 0, we are at the 165 million point. And as we go out 5, 10, 15, 20, 30 years, the amount of money, which is the y, goes up and up and up and up and up exponentially in this growing curving fashion. And as the years go by, I mean, it just really starts getting, we see the steepness, we see the amount that it rises gets faster and faster. So over the course of 1 year over here, we're growing by a lot more than closer to the bottom of this curve. So that's important to recognize and understand about the exponential functions. But before I talk forever, what were we trying to find? So, oops, go back to the question. Question at hand, back to the matter at hand. So, we want to know what year did it surpass 1 billion. So again, on our chart, that's going to be 1,000. So we need to find where it crosses 1,000. So the easiest way to do this, there's a couple of ways you can do this. You could look, but you're not going to get an exact number. Now, one handy way that we learned in class was just to type in here a line. Okay. Now, if you type in y equals a number like 10,000, for example, because we're looking for 1 billion. Make sure we got that right. 1 billion. And 1 billion is going to be 900, we're in millions, so 999 and then 1,000 equals our 1 billion. And I actually put this is 10,000. Okay. Oh wait, I want that on there for later. Okay, so you just type it in there like that, y equals, and hit enter, and that's going to give you a horizontal line because it's showing your all the way across at any x value, y is going to equal 1,000. So it gives you a horizontal line just like your x-axis. And vice versa, if you do x equals a number, you're going to get a vertical line. So we have this vertical line, and I'm going to highlight this blue one. This blue one is our 1,000. Let's get rid of the gray one. And what we're looking for is where does it intersect? Where does it cross our graph? So we can see here that at the value of y equals 1,000, our x equals 14.3889, and so on and so forth. So we know that that's 14 years from 1990. Okay. Now, going back to the question. We want to know what year. All right, so 14 years plus 1990 is 2004. Okay, so that's the answer to number 3. And when we go to number 4, the question is find the AROC, average rate of change, from 1990 to 95, 95 to 2000, 2000 to 2005. And we want to notice things about it. We want to see like make some meaning out of it and figure out like why, what is it, and how does it change, and why does it change in that way. So how do we find average rate of change? The formula for that is the change in y over the change in x, or the change in our output over our change in our input. Okay. Now, for me, the best way to think of this is the speed of a car, miles per hour. So, what does miles per hour mean? We're saying how much distance do we go in a certain amount of time? Okay. And if you were to graph that, your y value would be your distance, say 20 miles. Okay. And if you're driving a car really slow, 20 miles per hour, you're going to go 20 miles in 1 hour. So, uh, what we're looking at is the change between 2 points. So, um, the textbook and a lot of things that are teaching us this stuff, they put things in a little table so that we can look at it. Um, Now you can do this manually. You can graph it like we did, or you can plug into the formula the y value that you're looking for, or sorry, the x value that you're looking for, and solve for the y value, just like you would use the function manually. So like in this example, and I think it's better just look at this table first. So we're looking for in order to find the answer, we need these 4 points. So we need the data for 1990, 1995, 2000, and 2005. Now, um, 1990 in our graph and in our formula is represented by 0 years since 1990. So our first x value is 0. 1995 is 5 years later. Everything's 5 years later. So we have 0, 5, 10, and 15 for our x. Now for our y, we started out at 165. And if you plug in 5 into this formula up here for t, and you solve, you're going to get this 308.63, and so on and so forth for each one. Now, if you don't want to do it by hand or you don't have to, again, this is one of the reasons why I like doing things with the graph, because this site has a table built in. So like if I go to my formula and I click the little three dots, I can hit table of values. Um, or I already have it entered in, so it just pops up when I do that. But normally when I do this, and you can edit it here, you can change your parameters for this table here under edit. But when you first hit table of values, it's going to pop up this window, and it wants to know what are you looking for? What data do you want in your table? And for this example, we want to start the table at 0, and we want to go to 15. And in between there, we want it to go by steps of 5. And you can put anything in here. You could go to like 0.1. You can go all the way up to 1,000,000 for your X value. If you go too high, though, the software will break. It can't handle too much. But usually you only need a little bit, like in this example. So this is what we put in here, and it will spit out this, and it gives you your answers right here without having to actually solve for y every time. Now again, that procedure, you should know how to do it, and after you've done it a bunch of times, it's not that hard, but this is easier. So um, anyway, I just rounded these numbers off and I plugged it into here so we can understand it a little bit better. Um, Now we have these values, and we want to know what's the average rate of change between each one. So um, we need to plug it into this. So the change in y is what? It's the change from each point to the next. So it's just like this one with the y2. We have a y2 and a y1 and an x2 and an x1. I'm sorry I didn't write this down here, but you're going to write on the top of this thing the second y value, which here is 5, or sorry, 308.63, which I did here. Okay, minus the first or the previous y value, which is 165. And the difference of that is going to be divided by the difference of your x values. So the second x value is 5 minus the first x value is 0. So if you calculate that, you're going to come out with 28.7206. And I can't remember if I rounded that or not, but you're going to come up with a number like this. And it's important to recognize that this is millions of dollars per year. So what is it? It's not 28 million. It's not 28 years. It's $28.72 million per year. And that is the average amount that it changed each year over that 5-year period. So it changed a whole lot in 5 years, but on average, how much did it change each year? And now the actual change could have been more or less depending on your data set. You know, 1 year it might have changed a lot, and the second year it might have changed a little bit. But that's why we're getting this average rate. Okay. Now, you're going to do the same process for each one. So, like the second one is the difference between year 2000 and 1995. You got to remember to do it backwards. During your second one minus your first one, and second for x and y. Now this one we get a bigger number. We get 53, thereabouts 53 million per year. And the third one, doing it again, we get 100 million per year. So the question was, what do we see about it? Is it increasing, decreasing, staying constant? What does that mean? So we see that it's increasing as the years go by, and we look at select sections of our exponential function, sections of that graph. We see that the rate of change, the average rate of change between those points, it just keeps getting bigger and bigger. And in context, that brings us right back to what we were talking about in question number 1. Like, why would we use an exponential graph? It's because, more than likely that's the reality of the situation, that each year this business, or the NBA, is making more and more money. They have more and more money, so they're going to make more and more money. So we would see an increase in this average rate of change as well, not just the end result. Now, again, in reality, like a lot of businesses, they go down and up and down and up. Hopefully, over the long run, they continue an upward trend. If the business fails, it's just going to plummet and go completely down. But this makes sense given the information that we have, and it's the NBA. Everybody knows the NBA is. It started out and it just got more bigger and bigger, more and more popular. We know the players get paid more and more and more all the time. They get paid tons of crazy money. So just everything fits into what we know. That makes sense. And one thing I want to close with is, this is kind of interesting because, where is it at now, right? So our information gave us until 2018, which is not that long ago, at 5,005. Sorry, that is $5.5 billion, which is a lot of money. I mean, think about that. If you had a business, or even if you just made that much money per year, it's like almost hard to even comprehend how much money that is. But if you just Google the annual revenue of the NBA, the first result, it talks about $10 billion a year. That was between 2021 and 2022. So it's only a little bit after our data, and it's a little bit before now. But an interesting thing about this is, like, let's look at our graph and see if our graph matches that value. So if you remember here, I had this 10,000. That 10,000 equates in our scale of our graph to to 10 billion. Okay, so let's zoom out. I highlighted the orange, so that'll pop up again. Um, yeah, there it is. And you can see it's way up there. The graph is already super, super steep. Um, now, let's just see what it says. Okay, so at $10 billion per year, we see 32. Okay, and what's 32 years after 1990? So that's 2022. And what did Google say? The same thing, right? So, uh, this tells me a couple things. One, that our graph is our function is probably, I mean, mostly accurate. And two, that the data that we were given for this problem was based off of like real world data. So like our professor, somebody gathered that data probably from online somewhere and created this problem with it. So it's just pretty cool. And why would we even want to do this, right? I mean, we want to analyze things, figure stuff out, how it works, and also potentially predict the future. Now, you know, there's no surefire way of doing that. But we could say, for example, let's put in here x equals, today we're in 2023. That is 33 years from 1990. Let's let's go ahead and put in. We want to know 10 years from now, 2033. Okay, so that would be 43 years. So x equals 43. 43 years from 1990. And let's find out where it intersects with our graph. Now, 10 years is a long time, um, but it's not too crazy to assume that, if the monetary system is the same, if you got to figure there's a lot of factors like inflation and things like that. But if everything else stays the same, uh, we could assume that the amount of money that they would make a year would be it's like astronomical. So you 300 35971. So that's millions to billions. Add three zeros on that. So 1, 2, 3, 1, 2, 3. So that's 35 billion. Um, 35 billion a year. Again, 10 years is a long time. So like it'd be much easier to predict like next year, the year after that. 5 years maybe. Um, but you could have some reasonable assumptions about the future that way. Um, so it's one interesting thing. But anyway, this is probably video is probably super long. Hopefully, it will upload. Um, but yeah, that's community problem one, and I'm excited to see how everybody else did this. Hopefully, there's more videos. I think this video thing is definitely a lot more personable, and definitely helps for me anyway to really remember what I learned and really lock in what I learned. So, good stuff. Thanks to Professor Malley and if anybody actually stuck in for however long I made this video, thank you to you for listening. But yeah, see you around.